How's it going, guys? Today we'll be going over eigenvalues, eigenvectors, how to find them from a certain linear transformation, why are they useful, when are they used, and just checking to make sure you get the right eigenvectors after you've done all your math. So without further ado, let's get started. So first question we have to answer before we can get to finding them from a certain linear transformation would be, what are they? Are they useful, and what for? And so we can define what eigenvectors and eigenvalues, kind of coincidentally with eigenvectors, are by writing out the linear transformation of a certain vector. So with this equation, what it is essentially saying is that when a certain linear transformation is applied to the specific eigenvector for that transformation, it will give out the same vector but scale differently, which is the eigenvalue. So this is very useful when we have to use different set of vectors, not the x and y normal ones, to span the space. We will probably make another video on properties of eigenvectors and eigenvalues, why eigenvalues are always positive, why eigenvectors are orthogonal, all that good stuff, in probably another video, so I won't concern myself too much with this. But main idea with eigenvectors is that you're coming up with two different vectors that will span a new set of space according to this linear transformation, and it will not change under that transformation. It will only get scaled. This can also be used in data analysis, really reducing the amount of dimensions you have to make the data more usable and more easily to interpret. And so with all that, we can finally get into how to find them from a certain linear transformation. And so how about we just jump right into an example. So what we can see in this example is that we have a certain linear transformation, and we want to find what the eigenvalue and the eigenvector is. So going back to our old equation, right, we have t times certain vector a is equal to that same vector just scaled by the eigenvalue. If you solve this out for just the left, for the right side, we have t of we have that. And so if you want to factor out this vector right here from both of these terms, what we would have to do is multiply the eigenvalue by the identity matrix, as we can't subtract a scalar from a matrix, which is what a transformation is. So what we end up with is that. So from here, what we see is that either the eigenvector itself is equal to 0, which in this case we haven't really done anything and it's really not interesting to use, or this part's equal to 0, and this part will get us somewhere. So with that taken in mind, we can find out what the eigenvalue is by taking this part and setting it equal to 0. So when we do that, we have 1 plus I, 1 minus I, 0, minus, and then equals 0. So rewriting this, we have the determinant of 1 minus lambda, 1 plus I, 1 minus I, minus lambda equals 0. And so from here, what we can do is just take a determinant and set it equal to 0. So when we do that, we get squared. So that's this part, right? Now we have to subtract the second half. So we'll have 1 minus I, 1 plus I equals 0. And we see that this is going to boil down to 2. So this is going to go to 2. Which will come up later in this whole process. And we could just rewrite this as a quadratic formula, right? A quadratic function, sorry. And from here, we can just solve for two different values of lambda, which will correspond to two different eigenvalues. So we have lambda is equal to -2. Oh, sorry, we should probably work it out. because that was wrong actually, because we'll have minus 2 lambda minus, or plus 1 I should say, equals 0. And so we'll have lambda 1 is equal to negative 1, and lambda 2 is equal to 2. Alright, awesome. So we have our two different eigenvalues. We can see now why we have multiple eigenvectors and not just one, because we have two different scaling factors essentially. And from here, we'll have two different vectors that will span the same space. So we can get rid of this part, and let's go back to this idea right here. So we know what, we'll plug in a certain eigenvalue. We know what the linear transformation is, and we know what the vector is. So we don't know what the vector is, but we can solve for it, sorry. And so when we do that, we just plug everything in, essentially. So we have 1 minus I, 1 plus I, 0, A1, A2 is equal to negative 1, which will find our first eigenvector using this first eigenvalue, times A1, A2, right? Same vector. And now we can set up a system of equations, right? So A1 times 1 plus A2 times 1 plus I is equal to negative A1. And now we'll set up the bottom part. So we'll have 1 minus I A1, 0 times A2 is equal to negative A2. Awesome. So now we solve for A2, we plug it into the first system equation. So when we do this, we get, and then we plug it in, so we'll have 1 minus I times negative A1 is equal to negative A1. This, as you said before, was 2, so we'll have A1 minus 2A1 is equal to negative A1. Negative A1 is equal to negative A1. Now this may seem stupid and pretty obvious, but what this is pretty much saying is that we could just define what A1 is. We could define A1 to be 1000 and this statement will still be true. We can define A1 to be 0 and it'll still be true. Both cases will not really lead us to anything. So when we plug, we'll just do the simplified version. We'll just say A1 is equal to 1. So when we do that, we could then plug in A1 for here, and we would get A2 is equal to negative over, and distribute the negative, we'll get I minus 1. And so, that'll get us our first eigenvector from our first eigenvalue. We'll have 1 and I minus 1. Awesome. Now we can do the same thing with our second eigenvalue and find our second eigenvector. So let's do that real quick. We'll just change this to 2, and we carry out the same process. So same process. That times that times that plus that times that is equal to 2 times A1, and then 1 minus I A1 times that times 0 times A2 is equal to 2 A2. We solve for A2 by dividing 2 to the other side, and then we solve out for A1 by plugging this in for A1. And so what we would get from there would be A1 plus A1 plus 1I times 1 minus A1 times 1 minus I times A1 all over 2 is equal to 2A1. 2 here cancel out. A1 plus A1 is equal to, so we got 2A1 is equal to 2A1. As we said before, we'll just simplify this down for us, right? Because we could say it's 1000, but it's not going to get us anywhere. It will just be scaled by a certain amount. And so we'll just say A1 is equal to 1. And then from here, we can find out what A2 is. So we'll plug in 1 for A1, and we'll divide by 2 over. We'll get A2 is equal to 1 minus I over 2. And that will get us our second eigenvector. Okay, so how do we know that we got the right answer? So the main idea here is if we take our two eigenvectors right here and we take the dot product between them, the dot product between two orthogonal vectors, which two eigenvectors will always be orthogonal, if we take the dot product, the dot product should be equal to 0. So when we do that, we get, say, A1, E2 is equal to, so for those of you who are not really familiar with bracket notation, basically this is, we just take the complex conjugate and the transpose of it, so we convert it from a column matrix to a row matrix, and we take the complex conjugate of the complex part. So we'll have 1 times negative I minus 1, and then we'll lay it out as so. And then now when we take the dot product, so it's 1 times 1, 1 plus negative I minus 1, 1 minus I over 2. We can see now that this is going to be, let's see, negative 1, negative 2 on top, negative 2 over 2 is going to be negative 1, 1 plus negative 1 is going to be equal to 0. So we have checked that in fact these two eigenvectors are orthogonal, and so we can confidently say that these are our two eigenvectors for our transformation t is equal to 1, 1 minus I, 1 plus I, 0. Now, there are a lot of things we can do now from here. We can take a unitary matrix, take its inverse as well, and simplify this down to a diagonalized matrix. But that will be reserved for another video. This was really just having some fun with a few eigenvalues and eigenvectors. I hope you had fun, and I hope you learned something. Have a good day.